France Énergie Marine. I was the project leader of the POWSEIDOM project, and I am the co-leader of the NEMO project, a lead that I'm sharing with Julia Gottschall. And I am technically involved in both projects, specifically for the measurement aspect of turbulence with a Lidar profiler. So today I'm going to present some result, specifically result from the POWSEIDOM project, but I will also address some perspective and ongoing work of the NEMO project. So there is 4 parts. So the first part is some work dedicated to the enhancement of turbulence measurement with a prototype Lidar. So this is work we've done with Vaisala. So we applied this work on their technology, the WinCube V2.1. After there is some, the second point is the methodology that we developed. It was not in POWSEIDOM, it was in another project, but we did not get the opportunity to present it, so I will do it very quickly. So basically the idea of this methodology is to take for a dedicated area, what is the correct number of sensors we need to get enough information for the wind resource assessment, and where should we install this Lidar. So based on this work, we then deployed our Lidar in Le Planier Island. So this is in the Mediterranean Sea. So this is the third aspect of this presentation. And finally, I will present the preliminary motion compensation algorithm that we developed in the POWSEIDOM project, which is an alternative to the geometrical motion compensation algorithm proposed by some research institute or company. And I think Julia will mention this geometrical approach in her presentation. So the first part. So the idea here was so it was the beginning of the POWSEIDOM project. We contacted Vaisala to propose some enhancement of the Lidar. So basically, so for this WinCube technology, the sampling rate is for the line of sight velocity is 0.25 Hertz. So with this sampling rate, we can detect some turbulence eddies with the associated energy. But of course, if we increase this sampling rate, we think that we will be able to detect smaller eddies and the associated energy, and thus get turbulence measurement, and more specifically TI, that are more accurate, or I would say more close to the TI that will be given from a reference instrument, for example, the sonic anemometer. So Vaisala did the work and proposed an increase of the sampling rate by a factor of 4 in comparison to the commercial configuration. So we have a full paper dedicated on that. So I have sent the last version this month. So it is, I would say, 90% different of the paper. So the first version of the paper. Now the focus is on standard deviation and variance only, and a comparison to a MetMast, and a comparison to a commercial Lidar. So there is three measurements from 3 different instruments: a commercial Lidar, a prototype Lidar, and a sonic anemometer, which was the reference of this. So the first step was to prove, or just to prove that the prototype Lidar is at least able to provide mean wind properties that are similar to the commercial Lidar. And this is the case, actually. So you can read the paper once it will be published, but this is the first result of this. So the prototype Lidar is able to give mean wind properties that are similar to the commercial Lidar. There is unfortunately a low limitation, of the data availability by 0.5% for the old data set. So the data set was 47 days long. And for the aspect of turbulence, so you can see this on this figure, so where I'm plotting the standard deviation. So the prototype configuration, so with the increased sampling rate, is able to capture, we will say, 7% of extra energy, so that are associated with we think is associated with the smaller eddies. So this 7% is taking it into account the removal of the noise, and also we have employed the variance method for deriving this standard deviation. So it means I will say a few words about the variance method just after, but the only source of error here is averaging inside the probe. So we are not using the instantaneous velocity ux and uy, so which is called the standard method to derive ti and the variance. So we think that the 7% is the right number actually. So now, what is the variance method? So this is what new methods. Be careful about new method because we had something about this method, but this is the variance method. So basically, the name variance method comes from physical oceanography. So this is it was the topic of my PhD, physical oceanography and the characterization of turbulence for the development of tidal energy with ADCP. So we can see an example of ADCP here. This is basically a LiDAR, wind cube LiDAR profiler underwater. So my purpose actually for the wind world is to transfer some methodology that are used in physical oceanography to the atmospheric science. So, and the method I'm mentioning here is variance method, which is used since several decades. In atmospheric science, the variance method is not called variance method, but there has been some equivalent work performed by Eberhard in 1999. So this is a method we'd like to improve and implement for our measurement with a LiDAR profiler. So this method was compared to the method I called the standard method, which I would say is used by everyone in the wind power industry. So basically, people are using the ux and uy instantaneous velocity derived from the LiDAR profiler to compute the standard deviation and TI. But the problem with this method, there is four source of errors. This is the interbeam effect. So I won't go into too much detail about that because I think Julian will say a few words about this effect. But basically, the interbeam effect is a source of error because by using the instantaneous velocity, ux and ui, you are combining information that are collected at different time and space, which create, I would say, disturbed velocity spectra with underestimation or overestimation of the variance. The intrabeam effect is the volume averaging, which creates underestimation of the variance. There is also noise, which creates overestimation of the variance, and also the low sampling rate is an issue because we cannot capture the energy of the smaller eddies. And actually, the low sampling rate, if you want to increase the low sampling rate, it will feed the interbeam effect. So it will it could be worse actually to increase the sampling rate by using the standard method. There is an alternative, so as I mentioned before, the variance method. So with the variance method, since we are doing statistics on each position, so each line of sight velocity time series, so beam by beam, and after we are reconstructed ux and ui to get the variance along wind with this formulation, so you can see there. So basically, with this method, we don't have the interbeam effect, but we still have the intrabeam effect, so we cannot work on, or maybe we can work on, but it will be on this effect, but it will be another project. Also, what is interesting with this method is that you can plot the spectra of the line of sight velocities, and it is very easy to identify the noise, the instrumental noise. So this is basically the flattened portion at the highest frequency. So it's possible to identify this the polar spectral density of noise and deduce the variance of noise and subtract it to the variance measured by the line of sight velocity, and also increasing the sampling rate improves the methodology as well because we are working specifically on the different position, on different line of sight velocities. So comparison of both methods. So on the left-hand side, so let's focus on wind, on specific wind direction. So when wind is aligned with a pair of opposite beams, so for a wind cube, it's 1 and 3, beam 1 and 3, or beam 2 and 4. So when wind is aligned with this opposite beam, we can make the hypothesis that the cross term sigma xy is equal to sigma uv, and it is negligible. It is almost 0. So we can remove this because we cannot actually solve this term with only 5 beams. And this is, I will mention that just after. And you can see that in blue, this is the variance method, and in orange, this is the standard method. So there is so for this specific case, the variance method outperforms the standard method for every error metrics, MIE, RMSE, and R square. But unfortunately, on the right-hand side, so for all wind directions, so this is basically what's in the interest for everyone. So we cannot make the hypothesis that sigma xy is negligible because it is wrong. But the problem is we cannot measure it, so we don't have other choice that to make this term to be equal to 0 because we cannot measure it. And when we are doing this, so sigma xy equal to 0, we get the figure on the right-hand side. So the variance method in comparison to the standard method. Even with sigma xy equals 0, which is wrong, with this hypothesis that is wrong, we still have a better performance for MIE, RMSE, and bias for the variance method in comparison to the standard method, but there is a huge scatter. So it's not, this is not good, actually. So we need to work on that. And to work on that, the alternative is to measure sigma xy. So as I said before, with only one LiDAR, it's not possible because we have only 5 beams. So the idea will be to add an extra beam. But at this stage, it will be too long, and it's up to Vaisala or any other manufacturer to do such modification. But an alternative, and this is something I've done during my PhD with ADCP, is to combine actually 2 LiDAR profiler with one LiDAR oriented at 45 degrees in comparison to the first one. And with this specific configuration, we can resolve the full Reynolds stress tensor and thus get the cross term and apply the variance method for every wind direction. So what I will expect and what I will hope is that since sigma xy can be negative or positive, it will improve the R square. Because I'm expecting that it will be more along the black line of equality with the sonic anemometer. But let's see, this is an ongoing work in NEMO project. So we have collected the data already on the METMAST of the FECAM METMAST operated by France Énergie Marine. And I'm currently doing the analysis, and there is a paper in preparation for this specific configuration, but I don't know when it will be released, probably at the end of this year or beginning of the next year. Now just a few words about optimizing sparse sampling for offshore wind resource. So basically this is an area that are of interest for the development of the wind power industry in France, and more specifically, there is an area in the Mediterranean Sea. And the idea here was that if we are taking an area, how many sensors are needed to capture most of the information required for offshore wind resource assessment, and where should this sensor be installed? So we have a paper about that by my colleague Robin Marcil. And basically, we focus the study on different areas and in the Mediterranean Sea. And this is based on the Gaussian mixture model. I won't go into too much detail, but this is just to say that for the Mediterranean Sea, we found that the optimal sensor network is a 7 sensor network, and hopefully one of these location match the location of the Plani Island. So we decided to install a LiDAR there, and this is the third topic of the presentation. So we have now LiDAR certified. So this is a prototype LiDAR, actually. That is a prototype because the sampling rate is multiplied by 4. So this LiDAR has been certified by DNV in 2022. And it has been, just after that, we installed the LiDAR on Le Planier Island. So the Planier Island, the LiDAR is operating since December 2022 and is still operational at this site. And we have different measurement level above the sea, so from 60 to 220 meters. And one of the results of the POWSEIDOM was to characterize the offshore wind dynamics and for wind energy production in this area. So we focus on the wind direction, wind veer, wind speed, low-level jet, turbulence intensity, and wind speed profile for a 1 year data set, so 2023. And so we wrote a paper about that, which is a result of deliverables that we made public. So you can get this paper on open access if you are interested about the wind dynamics in this area. And basically, what we've proposed as a deliverable for our partner is a time series for the whole year of 2023 of wind speed, wind direction, and turbulent kinetic energy, turbulence intensity, vertical and diagonal dissipation rate as well. This is something I did not present, but we have a methodology to derive turbulence dissipation rate with the beam 5 with a correction of the noise. And this is something we can do actually for any period you are interested in. So don't hesitate to contact us if you are interested in getting this data. And the last point, maybe the most important part of the POWSEIDOM project, this is a preliminary algorithm. Because it is not ready yet. It is not ready yet because it has been only tested on a moving platform. So as you can see on the right-hand side, so this is a video. So basically, we installed a LiDAR on an hexapod, which was able to reproduce some motion of representative of a buoy, and a fixed LiDAR was installed nearby to provide reference measurements. We have a paper about this experiment, just present the experiment. Actually, another paper is in preparation. So we have 15 cycles of 3 hours long each, and one cycle was composed of 12 sequences with different rotation around different axes. So 1 axis, 2 axes, 3 axes with 2 different amplitude, 5 or 15 degree, and 3 different period, 4, 6, and 8 period, 8 seconds, sorry, and the amplitude 5 and 15 degree. And so we have a irregular motion. So this motion was the idea was we focus this irregular motion on a buoy called Mont Abiop, and the natural period of this buoy is 4 seconds. And we consider that we could install this buoy on the Fécamp Metmast area. So this is typically the periods and significant wave 8 that you can have in this area, and we produce this on the hexapod. So as I said before, so we did not focus on the reconstructed geometrical reconstructed algorithm, I would say, that is proposed. So we decided to work on the spectra of each line of sight velocity time series and identified automatically the part that is contaminated by the motion. So as you can see in blue, this is a fixed LiDAR. So fixed LiDAR is not moving, and the mobile LiDAR is moving. So it's very clear that the hump of energy at higher frequency is due to the motion. So we need to identify the part contaminated by the motion and remove it. And our algorithm is based actually on the fitting function. So we are considering only the part that is not contaminated by the motion. So for each spectra is different. So we have a cutting frequency that is moving automatically with the frequency and the period, with the period of the motion. And we are fitting this part and extrapolating the other part, so the fixed and mobile LiDAR. And once we get that, we are computing the variance of the extrapolated spectra by integrating the spectra for the fixed and mobile LiDAR. And then we are feeding the variance method with the variance provided by the extrapolation of the spectra. So we get TI derived from the variance method corrected from noise and corrected from the motion. So we get this final result actually. So before correction on the left-hand side. So basically we have a 100% error, relative error for the mean TI, and on the right-hand side with this method, the error is now 5%. So we have a paper in preparation about that, and there is also perspective of improvement. For example, installing 2 Lidar on a buoy and to get the sigma XY. For example, this is a perspective of improvement. So this is something we will do in another project. We hope we'll do that in another project. And that's it. Thank you for your attention. And don't hesitate to ask questions in the chat.